In this pre-calculus algebra video, we're going to talk about what's called the upper and lower bounds theorem, and we're going to use that to find zeros, amongst other tools. Okay, so first of all, the upper and lower bounds theorem, what it says is this, I'm just paraphrasing. It's when you're looking for the zeros of a polynomial with real coefficients, and what you do is you use synthetic division, and the conclusion is this, that a positive number is an upper bound of the zeros if the last row of synthetic division has no sign changes, and a negative number is a lower bound of the zeros of the polynomial if the last row has alternate signs. And let's see what's meant with some examples. So for example, let's show that 2 is an upper bound of the zeros of this polynomial, and negative 4 is a lower bound. So we want to show that 2 is an upper bound, and that negative 4 is a lower bound for the zeros of this polynomial. Now we're not showing that 2 and negative 4 are zeros. We're showing that 2 is an upper bound. That is, there aren't zeros larger than 2. And likewise, negative 4 is a lower bound. There are not zeros that are less than negative 4. Okay? And so what do? Well, for an upper bound, what you do is you take the number, the positive number, and use synthetic division. So you put a 2 on the outside in this case, and synthetic division, you draw this large upside down division symbol, and you write the coefficients, 1, 3, negative 4, negative 2, and negative 7. And just like before, right, bring down the 0, or bring down the 1, and you have a 1. So it's going to be 2, 5, 10, 6, multiplying, we get 12, 10, multiplying, we get 20, and 13. So 13 is the remainder. Now what's important here is that, well, two things. First of all, it shows that 2 is not a 0 because the remainder is not 0. But it also, notice that these are all positive. That is, the last this row for synthetic division, including the remainder, they're all positive. And that implies, because they're all positive, that implies by the upper and lower bounds theorem, that implies that 2 is an upper bound of the zeros. Okay, in other words, there are no zeros of this polynomial that are larger than 2. Okay, and likewise, let's show that negative 4 is a lower bound. So you negative 4, same thing. It's going to be 1, 3, negative 4, negative 2, negative 7. And for lower bounds, you're looking for these to be alternating in sign. So we have a 1, negative 4, negative 1, 4, 0, 0, negative 2, 8, and 1. And so it's positive, negative. Now, when we say alternating in sign, it turns out that you can include 0 to be positive or negative, whatever you need it to be. So I can think of this as positive. Well, let's put it this way. Not negative, negative. Not negative, negative, not negative. Okay? So a 0 can count whichever way you need it to count. So what we see in that case is that because they're alternating in sign, that implies that negative 4 is a lower bound of the zeros. Okay, in other words, there are no zeros for the polynomial less than negative 4. Okay, so how does this help us in factoring and finding zeros of a polynomial? Let's go and do some examples of that. So let's find all the rational and irrational zeros of this polynomial. So remember, we have a rational zeros theorem, which says that what you do is you take all the divisors of the constant term and divide by all the divisors of the coefficient of the leading term, or the leading coefficient. So in this case, the divisors of 4 are 1, 2, and 4, and we divide it by the divisors of, in this case, just 1, so positive and negative. So we have to consider the numbers 1 over 1, 2 over 1, 4 over 1, and the negatives of those as well. So let's start with 1. So we're asking ourselves, is 1 a rational 0 for this polynomial? So using synthetic division, we have 1. Let's see, it's going to be, listing the coefficients now. Just like before, it's going to be 1, negative 6, 4, 15, and 4. So we have 1, 1, negative 5, negative 5, negative 1, negative 1, 14, 14, and we get 16, and that's not 0, which means that 1 is not a 0. Okay, so 1 over 1 didn't work. What about negative 1? Is negative 1 a 0, a rational 0? So 1, negative 6, 4, 15, 4. So it's going to be 1, negative 1, negative 7, 7, 11, negative 11, 4, negative 4, and 0. Okay, because you get 0, that implies that negative 1 is a 0. So we found one rational 0. Let's circle it. Now remember that when you use synthetic division, this is the quotient. In other words, it's like dividing the original polynomial by x plus 1, and you get this quotient, which would be x cubed minus 7x squared plus 11x plus 4. And now you could ask yourself, even though negative 1 was a 0 of this, it may be what's called a repeated 0. A repeated 0 means that not only was x plus 1 a factor of the original, but x plus 1 might also be a factor of this. In other words, we're going to try negative 1 again with this polynomial using synthetic division. So let's try negative 1 again, but now using this polynomial. So it's going to be 1, negative 7, 11, and 4. So once again, all we're doing is we're accounting for the fact that x plus 1 was a factor of this, but x plus 1 might also be a factor of the remaining quotient, which means that x plus 1 as a factor would occur twice if we end up getting 0 again here. So let's see, it's going to be 1, negative 8, 8, 19, negative 19, and negative 15. Okay, so the remainder is negative 15, which means that negative 1 is not a 0. It's not a repeated 0. It doesn't occur again as a 0. But notice that the last row here is alternating in sign, positive, and negative. And what that tells you is that negative 1 is a lower bound from the previous theorem. It's a lower bound of the zeros for this polynomial. In other words, remember in this list over here, I was thinking about 1, negative 1, 2, negative 2, 4, negative 4. Well, this tells you that you don't have to think about negative 2 and negative 4 because there is nothing lower than negative 1. There are no zeros less than negative 1 according to the lower bounds theorem. So I'm still looking for zeros of this, but I don't have to worry about negative 2 and negative 4. So let's go on. Let's keep thinking about rational zeros. Let's think about 2. So I tested 1 and negative 1. Now let's test 2. Let's do that on the next page. So we're testing zeros of this, and we're going to test 2. Right, that's the polynomial that we reduced it down to. So 1, negative 7, 11, and 4. So it's going to be 1, 2, negative 5, negative 10, 1, 2, and 6. Okay, and that's not 0, which means that 2 is not a 0. So now we are wondering, of the choices, the 1, 2, 4, and 1, right, what we should do next. Why don't we pick, now remember the negative 4, this was positive or negative. The negative 4 is knocked out. So let's go ahead and try the positive 4. So positive 4, and what do we get? Well, let's see, 1, negative 7, 11, and 4. It's going to be a 1, 4, negative 3, negative 12, negative 1, negative 4, and 0. Okay, what that means is that 4 is a 0. So 4 is a 0. So far we have the zeros of negative 1 and 4. And notice that when you divide by 4, that leaves you with the polynomial x squared minus 3x minus 1. Okay. Now the question is, well, can you factor that? And of course you can using the quadratic formula. So in that case, you're going to get x is equal to 3 plus or minus the square root of 9 minus 4, and a times c is negative 1, all divided by 2 times a, which is 2. So we're looking at 3 plus or minus the square root of 9 plus 4, which is 13, over 2. Okay, and this yields 2 more zeros, right? So we end up with the zeros being negative 1, 4, and we have 2 more. It's 3 plus the square root of 13 over 2, and 3 minus the square root of 13 over 2. And so we have a total of 4 zeros, 2 positive and 2 negative. And that's how it goes when you're looking for zeros. You use synthetic division, and you look for rational zeros, and you're constantly making your polynomial smaller in degree. So at first I had a polynomial of 4th degree, and then 3rd degree, and then 2nd degree, and you can always use the quotient once you have a remainder of 0. And finally, once you get down to an exponent of 2, you can use the quadratic formula to find the remaining zeros. Now, so this would be the answer to our problem, right? These are our 4 zeros. And notice that we had 2 rational zeros and 2 irrational zeros. Now, notice that, and maybe I should have done this in the very beginning, that the original polynomial was this, which was, what was it again? I think it was x to the 4th minus 6x cubed plus 4x squared plus 15x plus 4. Notice that we have, according to Descartes' rule of signs, we have one sign change from positive to negative, and we have a second one. So because you have 2 sign changes, that means you have 2 or 0 positive zeros. You can predict that in the very beginning. Real zeros. And notice in this case we ended up getting 2. We ended up getting 4 and 3 minus root 13 over 2. So Descartes' rule of signs tells you that you either had 0 positive zeros or 2 positive zeros. And likewise, if you looked at p of negative x, right, that's equal to x to the 4th plus 6x cubed, if you plug in negative x, plus 4x squared minus 15x plus 4. And how many sign changes do we have here? We just have 1, 2. So again, we have 2 or 0 negative zeros. Okay, and in this case we ended up having 2, right? The negative 1 and 3 minus root 13 over 2. Let's see. Let me look at that more closely here. Yeah, that's correct, right? So 2 negative zeros because, well, negative 1, but also root 13 is larger than 3, so 3 take away that number will be negative divided by 2. Okay, so this is Descartes' rule of signs, which you can do in the very beginning to predict what you're going to be getting. Let's try another one like that that uses all these different rules and tests for finding zeros. So let's find all the real zeros of this polynomial. So first of all, let's start with Descartes' rule of signs. So we're looking at, let's see, we have 1, 2, 3, and 4 sign changes. So we either have 4, 2, or 0 positive zeros. Those are our options. And then likewise, when you look at p of negative x, right, it's going to be negative x to the 5th minus 7x to the 4th. Basically, anytime it's odd, it changes sign. So minus 9x cubed plus 23x squared. Anytime the degree is odd, you get a sign change. Plus 50x plus 24. And how many sign changes do we have here? Well, no sign changes, none. We only have 1. Okay, so now whenever you have 1, that tells you that you must have that number of negative zeros. So we have 1 negative 0. Okay, so we either have 0, 2, or 4 positive zeros and 1 negative 0. Now we're also going to be looking at now considering the rational zeros theorem. What you do is you take the original polynomial and look at the divisors of the constant term. So if 24, and you divide it by the divisors of the leading coefficient. So it's going to be, the possibilities for 24 are going to be, let's see, 1, 2, 3, 4, 6, 8, 12, and 24, okay? And the possibilities for the lead coefficient there are just, well, there's only 1, right? Positive 1. So this is what we have to test. Positive and negative, all these values for the rational zeros. Okay, it seems overwhelming, but let's go ahead and just start off and we'll see that there's some shortcuts. So let's start off with the easy one. Let's start off with 1. So we're testing 1 using synthetic division. So we take the lead coefficients, which are 1, negative 7, 9, let's see, 1, negative 7, 9, 23, negative 50, positive 24. So bring down the 1, and it's going to be 1, negative 6, 3, 3, 26, 26, negative 24, negative 24, and 0. Okay, and what that means is that 1 is a 0. So we found 1 0 so far. let's check to see if 1 is a repeated 0. So remember, this gives you a new polynomial, in this case of degree 4, right? So we're going to test 1 again on this polynomial. And it's going to be 1, -7, 9, whoop, take that back, 1, we're using the quotient here, 1, -6, 3, 26, -24. Okay, so is 1 a 0 of that polynomial with these coefficients? So 1, 1, -5, -5, -2, -2, 24, 24, and 0. It is, right? So 1 is a repeated 0. It occurs twice in this original polynomial. Okay, let's go on to, let's try -1 now and see what we get. So let's go -1. And we have 1, -5. Whoops, I'm taking the original polynomial now. So 1, -7, 9, 23, -50, and 24. Okay, so it's going to be 1, -1, -8. Oh, by the way, you could again try 1 on this. You'll find that it doesn't work. So 1 repeats twice, but not 3 times. So I just jumped to -1, but you can test 1 again on this, and you'll find that it doesn't repeat again. Okay, -1 and -8, it's going to be 8, 17, -17, 6, -6, -56, +56, and 80. Okay, now circling that, we see that the remainder is not 0, so -1 is not a 0. So now at this stage, we have to make a decision. Now look at all these different numbers we have to try, right? 1, 2, 3, 4, 6, 8, 12, 24, not 4, but 20. Let's write that. Should have been a 24 there. So all these numbers we have to try. Now you might say, well, we could just increase in order, right? And that seems generally like, an easy thing to do. But look, the numbers can get large even with small numbers. So you don't necessarily know just because the numbers are large that you're going to get large numbers in this line here with synthetic division. So what I'm going to do is I'm going to jump to 6. And the reason I'm going to jump to 6 is I'm hoping to eliminate anything larger than 6 because I'm hoping 6 is an upper bound. I'm trying to eliminate half or a bunch of numbers if I can, and then if 6 is an upper bound, then I can just focus on these lower ones. So let's test it out. So I'm testing 6 with it would be with the original. Let's go ahead and do that now. Oh, actually, I'm realizing that I actually made a mistake here. Do you see what the mistake was? It's that I tried -1 on the original, right? Now, why did I not have to do that? Well, because what you have is that when you divide when you do synthetic division here and you have a line here, that's the new quotient. That's the quotient that you get when you divide by x minus 1. So you can work with that new quotient as your new polynomial. So I didn't need to test -1 on the original. I could have simply tested -1, or I should have tested -1 on the result after the second repeated 0 of 1. That is, this should have been the row here, right? Because I'm trying to factor this polynomial at this stage. So let's go back and do that. Let me erase all this, and I'm going to test -1 on the polynomial with these coefficients. Let's go do that. And then we're going to do 6 on that as well if -1 doesn't work. Okay, so that's the whole idea with synthetic division, right? Is that you're constantly whittling down to get a smaller polynomial. You don't have to go back to and you shouldn't go back to the original polynomial. So I'm trying -1 with the polynomial with the coefficients 1, -5, -2, and 24. So what do I get? 1, -1, -6, 6, 4, -4, and 20. Okay, it shows me that -1 was not a 0 of that polynomial, but with that, I'm basically acknowledging that I'm using the smaller polynomial now with testing zeros. And like I said before, let's test 6 and see what we get. Let's go ahead and do that on the next page. So I'm testing 6 in this polynomial, right? So because this is the polynomial with the coefficients 1, -5, -2, and 24. So let's go ahead and test it. So we have 1, -5, -2, and 24. and we get 1, 6, 1, 6, 4, 24, and I get 48. Okay, the remainder is not 0, but notice that these are all positive, right? So these are all have the same sign. And what that tells us is that implies that 6 is an upper bound. Which means in that long list I had, 1, 2, 3, 4, 6, 8, 12, 24, there's nothing larger than 6. Okay, so I don't need to test 8, 12, and 24. So I'm going to go back to my list and I'm just going to test 2. So does 2 go into the remaining polynomial? Let's see. So 1, -5, -2, and 24. So bring down the 1. It's going to be 2, -3, -6, -8, -16. And I'm left with a remainder of 8. Let's see if I did that right. -3, -6, -8, -16. Okay, so that looks right. Our remainder is not 0, and that implies that 2 is not a 0. Let's test 3 on our journey. So now we have, let's see, 1, -5, -2, and 24. So we have 1, 3, -2, -6, -8, and -24. Okay, with a remainder of 0. And that means 3 is a 0 of the polynomial, and when you divide this polynomial by x minus 3, you get the polynomial x squared minus 2x minus 8. And now, of course, you can factor that using just by factoring, like we know how to factor trinomials, and you get x minus 4 times x plus 2. And then when you set that equal to 0, you find that you get 2 more zeros, 4 and -2. So putting it all together, we had the 0 of 1, right? That was a repeated 0. We end up finding that 3 was a 0 because the remainder was 0. And then finally we whittled it down to a quadratic, and we found that we get the zeros 4 and -2. Okay, so these are all of the rational zeros for our polynomial. Actually, we can say something stronger than that. So these aren't just the rational zeros; they're all of the real zeros, right? And the reason is because our theorem about the Descartes' rule of signs said that we expected 4, 2, or 0 positive real zeros, right? Now that includes the multiplicity. So in this case, 1 has a multiplicity of 2, right? That it occurs twice. It's a repeated 0. So this occurs twice. So count this as 2 zeros, 3, 4. So there are your 4 positive zeros. And then we have 1 negative 0. Now notice that, remember, our original polynomial was of degree 5. And we have, from what's called the fundamental theorem of algebra, you can only have up to 5, in this case, zeros, because that's the degree of the leading term. So in this case, we found all the zeros of the polynomial. There are no complex zeros, as we're going to be dealing with in future videos. Okay, so that's how you use Descartes' rule of signs, the upper and lower bound theorem, the rational roots theorem, and so on, to find zeros of real zeros of polynomials. All right, until next time.